So I guess I will introduce Mian. So it's a great pleasure to introduce Mian Zhang, who's CEO and co-founder of HYPERLIGHT Corporation. I guess I need to make a disclaimer for conflict of interest reasons. I am also involved in this company as co-founder and scientific board. Basically, Mian, a bit about his history. So Mian did PhD with Michael Lipson at Cornell before she moved to Columbia, and did beautiful work in optomechanics and silicon photonics in general. Joined my group as a postdoc. Actually came in maybe like a few days before or after I left for sabbatical, which was my top secret. I didn't want to discourage him, so he braved the whole year with me being in Netherlands. Started working on optomechanics, but then recognized some new development that were going on at the lab at that time in this material platform called Lithium niobate that he's going to tell you about today. So in the process, he got kind of more excited about that project than what originally we were set out to do, which was in kind of a space of sensing. Which I think still it was a very interesting topic, actually. Maybe we should revisit this at some point. And then did beautiful work that he's going to mention today on development of new type of electro-optic devices and modulators, in particular frequency comms and many other cool things in Lithium niobate platform. Published a lot of nice papers. I mean, some of these were actually supported by SICOM. Amir Hassan was involved in many of these projects early on and still is. And then I guess Mian was at a crossroad that, in my opinion, he could have gotten an amazing faculty position at top university in the US, but he decided to actually, take the other turn and ventured into entrepreneurship waters and started this company that now employs quite a few people and is doing really well. So I guess he's going to tell us probably a bit about both science and commercialization of the platform that he's been developing with his colleagues. So Mian, the floor is yours.
Yeah, thanks, Marco. Thanks for the intro. I'm very glad to be here. And today, I want to talk to you about the my work on ultra-low loss integrated electro-optic circuits. So as Marco was mentioning, the foundation of this work was really done at Harvard when I was a postdoc. So a lot of the work here today will be part of that work, but I always will also bring in some of new development that that we've been taking at the company. So, all right, let's get started. So just a little bit background about, let me see, sorry, do this one. Okay, just a little bit about HYPERLIGHT and where we are. So we are a spin-off company from Harvard since 2018. So that's now almost 2 years ago. And then our mission, just very simply put, is try to develop a scalable thin film lithium niobate photonic circuits. So we have an office, or we had an office between a very nice location between Harvard and MIT, where but with the sort of the recent COVID developments, actually most of us now work from home. Yeah, but we're still in Boston, so so it's a very sort of, I think that being in Boston, physically in Boston, and having access to the clean rooms and then also to the talents is a very critical part for the early stage of the company. So I want to start sort of the motivation of the talk with some interesting, I guess, facts and information I found on the internet. So what you can see here is a global backbone optical fiber network. You can actually see like there's a lot of cables that is underlying the ocean, and then also the purple colors ones are the new development that is started to take on recently. So there's a lot more development of these under ocean backbone cables for the internet in the upcoming years. This is largely driven by the sort of the growing demand from the electronics and also data processing side. Just also like to get a sense of the scale of these things. So if we I guess, take our location of interest near the northeast area, New England area of the U.S. So you not only have the submarine cables, but you actually have a lot of optical fiber connections also in the land. So this is terrestrial backbone fiber networks. And these fiber networks, these are still only showing sort of the fiber analogy of the highway. So these are still the high bandwidth, heavy load fibers. We're not showing like, you know, fiber to individual homes or things like that. And if you take, I guess, another zoom in and then zoom into one of the data centers. So this is some of the I guess is the forefront of networking technology development is in data centers, where you have a lot of computers, you have a lot of racks, but also the data within the data center and to the outside need to be constantly exchanged at very, very high speed. So for example, in a single mega data center today, one can expect optical fiber network port sort of number between from tens of thousands to a few hundreds of thousands. And then the fiber optical networking is, in the data center is also getting used in shorter and shorter distances. So it was more sort of used in the higher level switches, but now recent days it started going closer and closer distance just because of the data rate, it started increasing more and more. So if we look at the trend of the growing sort of fiber capacity, we see that it's basically around 45% increase every year, and this is following an exponential trend. And this is true for sort of both all optical ports, that means including within the data centers, and then just the backbone network, which is the sort of the heavy load traffic. The reason for this exact rate of growth is largely driven actually by Moore's law, which is about doubling every year. So that's about 45% per year. And you know, those sort of growing electronics demand is a fundamental driver for needing higher speeds for optical fibers. So, and this is basically shows like the technology that has been supporting this kind of growth. So in the there's a sort of more traditional approach where you simply increase the speed of each of the fiber, and this is growing also exponentially, but at about 20% rate. The early development of new technologies like wavelength division multiplexing very quickly at about 78%, even 100% for products in the early years, that sort of helped solving this problem of ever-growing need for optical fiber bandwidth in the early days, but it started to plateau as we are getting to sort of a year 2020. So this plateauing is actually really worrying, and it's actually quite fundamental. So we are actually hitting what they call is basically the nonlinear shadow limit for optical fibers. So this picture comes from a science review paper on optical fiber networking technology about 10 years ago now. So that's from 2010, and it's actually predicted pretty well of what we saw in the last slides. So the sort of fiber capacity started from, this is about 10 megabits per second, and it's continuing to grow at about this times 10 every 4 years trend. So you started with sort of improving fiber quality, and you introduced the EDFA, which is the fiber amplifier, so you can push more power and data. And then you introduced the wavelength division multiplexing, which uses different wavelengths to carry data through the same fiber. And then you also now you started getting to this sort of more complex regime where you use, for example, coherent techniques or higher level encoding schemes where you try to squeeze a little bit more bandwidth. But it's not entirely clear that what is beyond that. And this is, by the way, the purple line is what we see as the Moore's law driven capacity increase for internet traffic. So what they basically predicted 10 years ago is that at about 2020, we're going to hit a capacity crunch. And what that means is basically, this is a point where the initial fibers where we thought that was so much better electronics for transmitting data is actually going to fall behind electronics, but of course not in terms of transmitting data, but in terms of the data being generated. It's not entirely clear what's after that. So this SDM is basically for spatial division multiplexing. And a very simple word to put that is basically use more optical fibers. But there's a lot of problem with that, because using more optical fibers, remember this is growing at exponential rate. So using exponentially more optical fibers and exponentially more optical components has, of course, its problem like cost or energy problems associated with that. So how do we, I guess, what can we do for this problem? So if we take a look of a typical optical fiber link, you always start with some kind of electronic processor, and then you use that to drive this optical transceiver, which is basically a transmitter and receiver for optical fibers. And what it does is basically it converts on the one side of a laser signal into a modulated signal, and on the other side it receives and then converts the laser signal back to the electronic processor. So this is sort of the very fundamental parts of the optical fiber network. So in this sort of connections scheme, the optical fiber is just passive, so it doesn't really consume too much energy. A lot of energy is consumed in the modulator side and also in the receiver side, and also in the amplifiers that is bring up the lighting intensity in between. But as modulators, as optical transceivers start to penetrate into data centers, and that's where the majority of the power consumption is, the power consumption and then the speed for modulator is start to be a bigger and bigger problem. So if we take a look of the existing solution, so this is a picture of the modulator that you can still buy off the shelf from perhaps Thorlabs or from other optical communication companies today, and these are basically based on bulk lithium niobate modulators. So the lithium niobate material, particular material here, is used because of the electro-optic effect. The issue with the bulk lithium niobate modulator is that the chip is not really, or how to say, the device is not really integrated. And this is a problem where you also have energy consumption restrictions, and also the requirement actually to have the number of that to grow exponentially over the coming years. So what we really needed to do here is actually through integration, so similar to electronics, and through reducing the cost or increasing cost efficiency, that we wanted to have modulators that are integrated. And in this particular case, we are looking at a silicon integrated modulator. So this is sort of where the original silicon integrated photonics started, and people were really hoping that by using silicon, which is a very good passive photonic material, that you could use this material and leverage existing fabrication facility to be able to make photonic solutions the way like electronics scale. However, there's actually a problem. So as I mentioned, silicon is a great passive material, but it's actually not a great electro-optic material. So you can make waveguides, and then you can make passive filters or some functionalities like that, but you can't really make a very good modulator. So even after, this is more than 20 years now of silicon photonics development, if we compare their performance of today's integrated silicon modulator and then the bulk lithium niobate modulator, we actually see that the performance is still worse than those bulk counterpart. And this is not the case for electronics, because for electronics, by integrating electronics or integrating the vacuum tube onto electronics chips, the most important part is not just the size, but also the energy consumption that each of the transistor and also the speed that it increases associates with integration. But this is not happening in photonics, and this is also not really helping to solve the energy efficiency problems for sort of future low power optical network. So So what do we what options do we have if we really want to achieve low power, high speed, and low loss, and get us also integrated electro-optic modulator that does meet the next stage requirement? So this is where lithium niobate, this material that I mentioned before, that use a bulk material, comes in. So this material was used for bulk modulators for actually over 4 decades now, for really good reason. So it has very high optical refractive index. It has the most important part is that it has large Chi2 nonlinearity, which is basically electro-optic effect. If you apply a electric field, it's basically change the refractive index. It also has a wide transparency window, so from visible all the way to telecom. So that's sort of a necessary condition to make this this material usable for telecom. And in addition to that, it actually also enables a lot of other functionalities. So this is a sort of derivative solutions from the electro-optic modulator basic components that has sort of there's also lithium niobate is also, just by the way, it's also a Chi3 material, which is has interesting nonlinear optical effect. So we'll talk a little bit about that later stage in the talk. But for now, let's focus on the aspect, which is the electro-optic aspect of this material. So the goal here is we want to take the best electro-optic material, which is in this case would be lithium niobate, and let's see if we can make integrated modulators that has greater bandwidth. So try to hit a target of 100 gigahertz, which is the bandwidth needed for next generation optical, and at the same time achieving a low voltage. So in the conventional lithium niobate modulator, so basically a modulator that is looks like this, and this is also about 4-inch or 10 centimeters long. In this traditional bulk lithium niobate modulators, the reason they are quite large was because their waveguide is actually formed by ion diffusion process, which is resulting in a low index contrast, in this case about 0.02, and a large optical mode size. So in this case, it's over 10 microns in diameter of the optical mode. Now what this means is the waveguide has very large bending radius, usually on the order of millimeters. So on any sort of a meaningful size of photonic chips, you can't really bend the waveguide around or make meaningful complex structures out of that. So this was sort of fine for the older generations of modulators, but what we really wanted to do is, to make integrated waveguides similar to that of a silicon photonic waveguide. It's basically a nanowire that guides the light, and in which case you can achieve much smaller bending radius. So if you were able to microstructure lithium niobate, you will be able to achieve the index contrast between 0.72, and what that gives you is a subwavelength light confinement and also bending radius of less than 20 microns. So there is quite a big development in the early 2010, so which is about 10 years ago now, on this particular structure, which we call it LNOI, or lithium niobate insulator platform, where a thin film of lithium niobate is actually wafer bonded on top of a silicon wafer with a glass layer in between. So this structure is really crucial to realize the channel waveguide structure shown here, because in a bulk lithium niobate, if you just make a ridge on top, then you would still have leakage towards the bottom. So it's very essential to have a thin film to begin with. And this is where sort of the commercial, it started to be commercially available for the thin film around 2010. And that really sort of kicked the effort on lithium niobate research off. So of course, the sort of the idea of making nano waveguides on lithium niobate or etching lithium niobate was not a a very difficult idea to come about. As I was mentioning, the first reason that that people, over the decades of the bulk lithium niobate age, that this wasn't took off. The first reason was that the thin film was not commercially available, so it's only a handful of labs in the world can produce thin film. But there's also the other side of the story is, or the second half of the problem, is that lithium niobate is actually very difficult to etch. So this image here, which is SEM image, is a waveguide that we etched in the relatively early days of lithium niobate research. And this was actually already optimized quite a bit for the etching quality. So in this particular case, you can actually still see that you end up with a lot of roughness. And then the sort of the optical loss here is about 3 dB per centimeter. So it's basically attenuates by 50% over about 1 centimeter long waveguide. So, so this was okay. I think this was okay for research. But if you really want to answer the question, is lithium niobate a meaningful solution for the next generation integrated photonic circuit? 3 dB per centimeter is not really there. Because what this means is for practical performance levels, it will still be similar to silicon photonic solutions, which means overall, the extra effort you have to spend to develop on this material doesn't really worth it. So this situation completely changed when we, actually this work was done in late 2017, and the paper got immediately accepted. So it looks like this paper comes before that, but the result is really after that. So what we were able to do is actually we find actually using standard silicon solutions, silicon modulators, silicon processes, you can actually make optical waveguide that are very, very smooth. And what this leads to us is the loss improved, actually the attenuation coefficient improves by almost 100 times to about 3 dB per meter instead of 3 dB per centimeter. And this is a really big milestone, because what this really means is now you can almost build photonic circuits on your small chips, which are much smaller on a meter scale, and then really just ignore the loss and then really try to get the best electro-optic or nonlinear optical performance out. So the way we verify the loss at this number was that we made basically a micro-ring resonator which circulates the light around, and we measured the line width of that resonance. And in this particular case, we measured a line width correspond to a Q about 10 million, which is basically where this 3 dB per meter comes from. And we also get very good Qs for visible frequency as well, which is not normally used for fiber communication, but it has other kind of applications. So that was the sort of the basis for really the integrated modulators. So now we have a optical waveguide that we can basically almost ignore the optical loss. So the next question is, what does this mean for optical modulator? So when you have a waveguide on lithium niobate or on an electro-optical material, the process of making an electro-optic modulator is actually extremely simple. So all you have to do is that you put metal near between on the two sides of your optical waveguide, and you let the electrical field propagate efficiently in the optical mode, and then to achieve a good overlap between the electric field and optical field. And then the presence of electric field would cause a phase shift in the optical waveguide. And in this case, we have a MZI interferometer, Mach-Zehnder interferometer, which would translate this phase shift into a optical intensity modulation. So in this particular case, we got a Vpi, which is a half-wave voltage. That is the voltage needed basically to make the switch from completely off to on. And then now we achieve a Vpi of about 1.4 volts. So remember that the number I gave for the commercial modulators was about 3.5 volts. So that was actually after many decades of optimization, where this 1.4 volts was sort of the very first device that we are able to make. And then at the same time, while we achieve this sort of low voltage, what's really important here is that we're actually also able to achieve electro-optical bandwidth that is superior than what the commercial modulator was able to do. So in this case, for the 1.4 volt modulator, we achieved a 3 dB optical bandwidth of over 45 gigahertz. So this is already very similar to what the electro-optic modulator, the commercial modulator was able to do before. And we show like if we design a modulator to have a similar voltage as the previous commercial modulator, it's about 3.5 and 4.5 volts, we can actually achieve a bandwidth of over 100 gigahertz. So yeah, just add a little bit. We also recently demonstrated that this voltage, where before was measured at low frequencies, that at microwave frequencies, it's also similar similar levels. So we basically take these modulators and we work with our collaborator at Nokia Bell Labs, and we test this modulator in a real world data transmission experiment. So in this particular case, we encoded the optical modulator with 100 gigabits per second signals, and also with 70 gigabits signals, but with different level of modulations. So these diagrams are called constellation diagrams and eye diagrams. So what's really important here is that the upper signal basically corresponds to 0, and the bottom basically corresponds to 1. And what's important here is if you draw a line in between, that's basically how you make the decision on your data is 0 or 1. So having little overlap between the two lobes is very important to achieve what this called is the low bit error rate, which is basically low error rate in a data transmission. So for the 100 gigabits per second experiment, we got about 7.8 times 10 to the minus 5 bit error rate, and which of course can be corrected. In the 70 gigabaud signal, so that's a symbol rate, we have 4 levels. So this would basically means 2 bits per symbol that we're able to do 140 gigabits with 4 levels. And in this case, the bit error rate is actually a little bit better. And then for the 8th level signals, you can see there's significant overlap between these lobes. The bit error rate now is about 1.5%. So this level is still below the threshold for standard error correction schemes, which can correct errors up to a few percent. But of course, the panel here is that 210 gigabits signals, you also need to spare 20 to 30% of data to correct for signal correction. So the important message here is that it shows like the modulator it's not only works well on paper, but it also works for practical data transmission scenarios. So the next step of this, which we're currently working on, is to make IQ modulators, which is basically not only modulate the intensity, but also utilize a phase degree of freedom that basically use parallel modulators where you can squeeze more data in through a single optical wavelength. So looking at the figure of merits for these modulators, now when we compare with the traditional modulator, so the important performance improvement here is really on this trade-off diagram, where you have a trade-off performance between low voltage and high bandwidth. So for example, traditional lithium niobate modulator is somewhere, excuse me, somewhere along the 10 gigahertz per volt performance line. So what this means is that the modulator, say, if you try to achieve a 1 volt VPI or 1 volt operating voltage, you would only be able to get 10 gigahertz. So our first experiment has brought this up to about 30 gigahertz per volt. So we are basically pushing up the bandwidth by 3 times without sacrificing the voltage. So that means now you can operate in this sort of CMOS level voltages and still have a significant electro-optic bandwidth. And then the reason for that is basically if you compare the traditional modulator on the right with the integrated modulator, that by shrinking the optical mode size, you can put the electrode significantly closer, which increases the efficiency without losing bandwidth. And also as a benefit, you get the chip, which is the integrated modulator shown here as a chip, much smaller size than the traditional counterpart. So just to technically summarize this, compare with the more popular platforms of silicon and 3-5 materials and also lithium niobate bulk materials, the thin film platform is achieving really the best of all those parameters of all these sort of different options. But the important thing is it can achieve all of the optimal performance at the same time. So there was still an outstanding challenge. There was still an optical challenging is that by moving from the bulk platform to a thin film platform, the optical waveguide size actually become significantly smaller. So this was a problem where the optical insertion loss was still around 11 dB, even though the on-chip insertion loss is really low. And most of that was originated from edge coupling. Excuse me. So to solve that, we basically designed a efficient optical mode converters that pushes optical mode from the sort of the very highly confined lithium niobate into a sort of a channel waveguide structure, and eventually using inverse tapers to push the mode out. So in this case, the mode size didn't increase a lot, but the mode index has been lowered so that it matches with an optical lens fiber. So, so in this particular case, we're able to actually decrease the fiber loss from 11 dB all the way to 3.4 dB with current commercial solutions. So, so the optical modulator was sort of the for electro-optic manipulation. This sort of performance improvement is important for it's important for the near-term solution of optical fiber networking requirements on lower energy and higher bandwidth. But in order to meet future demand, to meet the continuous growth demand, we also need to think about completely new architectures. So in the next part, I want to talk a little bit about the new type of structures and functionalities enabled by this integrated platform that could change fundamentally how we do optical communications. So the example here is a frequency comb. A frequency comb generator, which basically is a equidistance spaced optical carriers in a frequency domain. And in a particular case for optical communications, you can encode signals in each one of these different colors of light. So this technology, or it's not really the frequency comb, but the technology where it utilizes parallel wavelengths of light to push more data through single fiber is actually used in every single backbone network that I showed, both for terrestrial and long haul applications. In every one of those scenarios, what is happening there is they use this technology called DWDM, which is basically a dense wavelength division multiplexing technique. So in this case, different colors of light is multiplex through a multiplexer, and then combining to the single spatial mode, and in the end, it's being split again and then detected at different channels, so there's no interference. For these systems, you need many modulators and you need many lasers and also sort of many electro-optic components to be on both ends, although you only use a single fiber. So this is one particular example of actually a long haul fiber rack that you can see, like this whole sort of fridge size component rack can basically support a few fibers. So is there a way that we could make simplification or dramatic simplifications to this system and then made it more integrated? So we think like the really important method here is to reduce the system complexity and then find a way to solve the need for parallel lasers, detectors, or making them more integrated. So if we take a look of how we could generate those kind of carriers with a integrated component, so we look at this particular case for generating frequency comb using electro-optic method. So what you can do is you can take a single wavelength of light and then you put this through a electro-optic material and then you perform phase modulation on this material. When you modulate, you will generate 2 optical sidebands. And then when you modulate it very strongly, the modulation will actually cascade and you will generate more and more sideband. So this is actually one way to generate a frequency comb. So in this particular case, the number of combs you generated is it's inverse proportional to the voltage that your modulator needs. Basically, the stronger you can drive the modulator, the more number of comb lines that you can generate. So for our modulator, because the voltage is actually quite low, so in this case, we were actually able to generate about 20 to 30 modulated signal lines, whereas in the sort of the traditional standalone modulator, you can probably generate around 10. So this is already quite interesting for a lot of communication applications to use just a direct integrated phase modulator as a comb source. But there is a potential challenge here, is that the comb lines are not exactly the same intensity. So none of them are really, unless these are flattened out, they are not particularly useful. And also the comb span is still relatively small. So now utilizing the fact that we have a small bending radius and then we can make complex photonic structures now on a chip, so we can actually put this electro-optic material inside an optical cavity. So in this case, what we do is we actually try to match the electro-optic modulation with the free spectral range of the optical cavity so that the modulation or the sideband generation is dramatically enhanced. So in this case, the cavity we made is a micro ring resonator. So we have a micro ring resonator and we have the phase modulator, which is basically 2 electrodes on the 2 sides of the rings, and then we modulate this at microwave frequencies that matches the free spectral range of the resonator. So in a resonator that we designed, which had a 10 gigahertz free spectral range, this is actually the comb spectrum we generated. So you can see that we have a visible spectrum with a comb that we can basically see on an oscilloscope spanning over 100 nanometers with 10 gigahertz spacing. So that's about 1,000 comb lines here with a single laser and a single microwave drive. And then the line-to-line intensity variation is actually only about 0.1 dB. And with the same resonator, we could also drive it at the higher harmonics of the micro resonators. In this case, we drove at a 3 times the harmonics, which is about 31 gigahertz, and you can basically get a comb that is 30 gigahertz free spectral range. So this kind of reconfigurability could allow you to use these combs for different scenarios where you might want different comb spacings. So now we have a comb source and we have a modulator. So we wanted to see if you can try to combine these two processes on the same platform. So in this particular case, we actually use a slightly different comb generation method, but that's a relatively minor detail. But the important thing is we start off with the frequency comb, and then we have a electro-optic filter, and at the same time, because of the electro-optic effect, it's also a fast switch. And then we can use this filter to pick out the particular comb line and then perform optical modulation on that. And this is basically goes along with the concept where I mentioned, where you start with a single wavelength, you generate a comb of frequencies, and you have an array of modulators, and in the end, you multiplex everything into a single fiber. So in this picture was shown by a different group. This was involving many different materials, but we want to try to simplify this with as much as possible onto a single platform. So what we did here is we basically pick up one of the comb lines we generated, where before the pump line was about 30 dB more than the signal line, but after the filter picking up the signal, the comb line was much higher than the pump line, and we can also select which comb lines we pick out by simply applying a DC voltage. In this particular case, we did a modulation at about 400 megahertz onto one of the particular particular comb lines. The bandwidth limitation here was because we use a micro ring resonator, which has a limited photon lifetime. Of course, the proper way to do this is that we would want to put our modulator designs with the sort of the Mach Zehnder traveling wave high bandwidth design beyond the sort of the micro ring resonator that generate a comb to really perform sort of high speed modulation. So all of the work so far I discussed was basically done at Marco's lab at Harvard, and this sort of a very nice demonstration, early stage demonstration, that even in a university research lab, we are able to integrate components with different functionalities onto the same chip, and then perform more complex scenarios where it's not possible to do in old platforms. But in order to bring this onto the next level, or try to bring this onto the commercial market, or to sort of realize more complicated device, we have to dial back a little bit and ask ourselves, is lithium niobate actually a fundamentally scalable device? Because we've seen like there's a lot of research, especially on new materials, that is easy to get one or few heroic devices working, but it's very hard when you try to make it into a larger scale device, or try to make many components working together. So lithium niobate, since it's the appearance of the thin films, many research groups along with Harvard has been working on sort of etching and optimizing the material processing, and people are able to get very good low loss as us as well. So one very common techniques everybody use here is that we all use electron beam lithography, which in nature is serial, that was able to support sort of masking requirement and support the line edge roughness requirement. There are a couple of groups that use photolithography, which are much more scalable, but they have to involve complex polishing techniques because the etching was not as smooth. And then by doing this polishing technique, you dramatically reduce one is the throughput, second is the controllability of the geometry of your particular structure. So what we really ideally wanted, is that we want a fabrication that is high throughput and achieve low loss at the same time. So this is the sort of the work that we've been taking on a little bit at HYPERLIGHT, is that we have been looking at high throughput, scalable, deep ultraviolet lithography of lithium niobate wafers without polishing. So here we are basically using very conventional techniques where we put the UV resist and then we expose and we etch in a very traditional silicon manner. And we want to see if this method could work, because if it works, it means like this material fundamentally is scalable, and then getting large-scale devices working is possible. So we're very excited to share with you that this is actually indeed possible, and actually we achieved very similar level of etch smoothness on this deep ultraviolet lithography processed wafer as E-beam. So very similarly, we also made micro ring resonators. In this particular case, we got a quality factor of 1.3 million, and intrinsic 1.8 million. So in this particular case, it's about 0.27 dB per centimeter. So it's not really at the 3 dB per meter on the E-beam level yet, but it's already significantly better than silicon, and it's definitely good enough for a lot of applications already. And we also know like there's many ways to sort of keep improving the etch quality. So what we also get from the wafer processing is that we now can actually do wafer scale characterization and see how the optical loss changes across the wafer, and also what kind of etch uniformity we get. So this is sort of the lithium niobate wafer before processing, and this is the lithium niobate thickness after processing, and here is the variation. So we can see that the film actually had about 20 nanometers of non-uniformity to begin with, which the manufacturer of the wafers is still improving them. And after the etching, we see that the thickness uniformity did not change very significantly. So now if we actually take the difference of these two, which gives the right information on the actual etch on the non-uniformity due to the etching, we see that we have about 20 nanometers across the whole wafer, but around the center area of the wafer, we have about only about 3.2 nanometers standard deviation in etching. So it's quite uniform, and we can probably do some more optimization so that the wafer edges are also more uniform in etching. But this shows like there's nothing really special about this wafer processing, that with optimization, there's definitely ways to get the whole wafer very uniform and flat. So this is quite exciting news, because if we take a look on this frequency comb result that we get before, and I was mentioning that one of the drawback here is the power is actually not very flat. And I also showed you another way that you can use a micro ring resonator to generate a much broader comb. But you actually also pay the expense there, is that your comb conversion efficiency actually is much lower. It goes from about 50% in this case to just about 3%. So you get a wider comb, but you get a much lower efficiency. So there is another way that you could generate a frequency comb still having a very high efficiency, is you basically cascade these electro-optic modulators. So what you need to do is you need to basically having, in this particular case, 3 modulators. So they have one lithium niobate here, and then 2 other lithium niobate here as phase modulator, and 1 as intensity modulators. With 3, you can actually shape the modulation so that the comb you get is very flat. So this is actually their spectrum with 3 modulators, and then you get about 6 nanometers, and then here is about 15 lines or so of comb. Of course, this is much broader, but this is after they have to pass through this with optical amplifiers and nonlinear broadening. But for apple-to-apple comparison, just looking at comb generation. For us, the really nice thing is actually we can integrate all of these comb generators on the same chip. So, the key advantage here is low optical loss in this waveguide. So the total loss through this whole system is actually much smaller than 3 modulators cascaded here, because the cascading of the 3 modulators here will generate basically around 15 to 20 dB of optical loss, in a system where the on-chip loss is less than 1 or 2 dB through the whole modulator series. And then according to theory, this is sort of the number of comb lines we could generate compared with what is already out there. Of course, the challenge, again, this is not a particularly difficult concept to come by, but in order to make this device, you cannot just make a heroic modulator or a heroic phase modulator or intensity modulator. You have to make 3 modulators cascaded in a row, and all of them have to work. So this is where we sort of used our improved or scalable fabrication technique, and in collaboration with Marco's group, that we made a integrated frequency comb generator out of several modulators, and then we are able to generate very flat comb lines on a single chip, and it matches very well with theory. So this is some initial results that we got very recently, and you can imagine sort of the future of this is really to take this comb generator here, for example, you can generate the comb frequency comb here, and you can use a micro ring resonator to pick out individual lines and then pass through very high bandwidth modulators. And this is essentially the kind of functionalities that I showed you that was completed in the sort of the whole fridge setup. And now this is possible to think about this on a single chip. And of course, just as a disclaimer, here we do not have a lot of the electronics component, and we do not have a lot of the control element that is needed. So the whole system will likely be bigger than this, and it may still be rack size. But what's important here is that this kind of geometry and this kind of new integration method would allow you to build much more complex system on a chip that hopefully can solve the issues, the urgent issues that optical communication is facing today. I think I still have more slides, but I think the time is up. So I think I will probably just summarize here, and yeah, I'll probably just summarize here and leave some time for questions. So what we basically show, like lithium niobate integrated photonics, in particular modulator, could be a very powerful solution for future high-speed applications. And we show that the low-loss etching of lithium niobate circuits are fundamentally scalable. There's the part which I didn't talk about, but I'll list out the reference in the next slide, is that the scalability and the integration of new functionalities could also enable this platform, lithium niobate, to solve high bandwidth and complex electro-optic and nonlinear optical functionalities. So just to quickly go over the references here. So in the very beginning, I talked a little bit about the low-loss platform and then the modulator platform. So what we and then also how we generate electro-optic combs. So what we didn't have time to cover was nonlinear optical part, which is also another important part to manipulate optical properties directly in the optical frequency domain, and also some kind of cool new functionalities as a result of very low loss, and also as a result of you can basically engineer the photonics state when you have the ability to make complex structure with small bending radius on the chip. So with that, I would like to thank especially Marco's group, and then all the group members there, and also the team at HYPERLIGHT. And I would also like to thank our collaborators at BBN, Raytheon, Columbia, Nokia Bell Labs, Stanford, and also Photonic System Inc. For collaborations and also giving us critical feedbacks. So that's the end of my talk, and thanks for your attention.
I don't know where the reaction button is to give you virtual applause, so I guess I'm going to give you a real applause. Thank you, Mian. There is a 2 minutes for questions, I suppose. I'm not sure if there were any questions in chat. Okay, there is, thanks for the note and some necessary consideration of technology transfer from the academic research lab to commercial publication. Can you speak to how you and HYPERLIGHT approached the challenge and got very nicely devised with commercial techniques? It's a question from Christina McGann. I'm sorry, my pronunciation wasn't very good. So commercialization, yeah. Maybe you're muted because I don't hear you.
Yeah, yeah, that's a very nice question. So, so just to be like completely transparent, we are still using a lot of sort of academic tools. I mean, that's including Harvard to do a lot of work now. But there's also significant changes. I think the biggest change is that in the sort of commercial approach, you really try to come up with a best, I guess, a team or particular structure or a particular priority that to achieve a certain technical or a product goal. So this is quite different from research where you need to think about publications, you need to think about research projects. So in the commercial side, we're able to focus much better on albeit much narrower problems. So that was sort of what I think enabled us to tackle the scalability problems. If that's answers your question.
Maybe if I can also add to the question.
Sure.
Maybe in terms of mechanics of how you reach there, and if I can make a plug for PSI and SEMLIS, which is actually deadline is coming up, and do you want to speak to that a little bit? Kind of just mechanics. Why did you start, and how did you get where you are right now?
Sure. So yeah, sorry. So when you bring the PSI deadline,
the Rockwell PSI and
oh yeah, sure.
When and why to start and things like that. You know, I think it's a very nice story.
Right. So I think I think for myself, just speak a little bit of my experience. I think I was a postdoc in Marco's group. I was setting my mind on trying to apply for faculty, I think at the time. But I think we had basically people and customers, now it's called them customers, but they showed sort of some kind of unusual interest from a typical scientific research that basically they flew into Marco's office and want to purchase the particular chip we published the paper with a huge amount of dollars. So that's sort of the point we realized we are really solving a problem that people really urgently need a solution. And I think what I personally really liked about that part is that because the moment, it's very different when people doesn't have to pay you and then does have to pay you. If they don't have to pay you, they will always tell you your work is very nice. Now when they pay you, they will tell you the part that does not work. Of course, they will also tell you the part that actually did work for them. So that part to me was a new experience at the time, and I really enjoyed it. So I think that's also when we learned about the challenges of current modulators and sort of what the problems we have been solving. So I think in a particular case, Marco was mentioning Rockwell Collins, so they were the first approachers to our technology. And I think that's what really changed sort of my mind. And I think a few folks in HYPERLIGHT as well to decide to start this company. And then now we started the company, and then because this, the particular, I guess the particular technology or the particular chips we make is in a chain of many components that's complex, important functionalities. So we also need to work with our customers to make sure we fit the timing, fit the goal, the scope, and then fit all the purpose and really solving their problem. So yeah, so I think this sort of very object or goal focused sort of approach is what I think to me is the most different aspect of the commercial approach, where there's the research phase.
It's great. If I can also maybe just add to this, I know we're running out of time, but it's timely plug. I think what really helped us at the beginning also was that Harvard has this very nice program called Physical Sciences Incubator. That basically, if you have a good idea, they give you, I think it used to be about 100K to kind of debug one point of your technology and allow you to kind of go and talk to VCs with more kind of confidence, I guess, that things will work. And so we were, I think Mian and Zhang at that time, another student in my lab. I think this was the first, were you guys the first technology kind of hard tech, let's call it, startup that Harvard put some money in? It was mostly,
yeah, I think we were one of the first few semiconductor startups.
Joanna had one or two others, yeah. So that and the deadline for that is when? This Friday. So if you have a great idea in the next 2 days, I encourage you to submit this to Office Technology Development and get 100K and start your own thing.
Yeah, actually, that's a very good point. Sorry, I forgot to mention that. That was, I think Harvard OTD was the first point, I think, for me to get a contact in a startup scene and talking to VCs. And I think that's really helpful sort of in terms of helping us to learn what is needed and what questions we need to answer, and then what kind of steps it does take to take a research idea into commercial product. So that was really, really helpful. So I definitely encourage you to apply for Harvard OTDs. Just talk to them or apply for their grant if you have some thought or if that's interesting to you.
Thanks, Mian. I guess we're done with time, unless there's a pressing question. I guess maybe I'll turn this over to SICOM folks.
Yeah, I don't see any other questions. And we'll be posting this to our YouTube channel also if anyone missed the talk or wants to go back and look at it. Great. All right. Thanks, Mian.
Thank you
okay,
so
great.
much.
Thank you.
Thank you. Thank you so much. Bye.
Bye.